This is lesson 14 in our Calculus 2 series, Approximate Integration. In this lesson, we learn to approximate definite integrals because some functions are not the derivative of any others, so we can't find an antiderivative for them. For example, when we look at the integral of e to the x squared is not the derivative of any other function, so we can't continue from here. Same thing is true for e to the negative x squared over 2. But this function in particular, e to the negative x squared over 2, is important for us. If we put a 1 over square root of 2 pi in front of it, this is the standard normal curve. And definite integrals of this function give us the area under the standard normal curve between x equals a and x equals b, and that gives us the probability that the variable lies between x equal a and x equal b. So being able to compute definite integrals like this is important to us. And if we can't compute them by taking an antiderivative, we need another method. So we're going to talk about methods of approximating definite integrals. And in this lesson, we'll use a simpler example, integral of e to the x squared. And to begin, we want to first recall our Riemann sums. When we first talked about the definite integral in Calc 1, we learned about Riemann sums. We said the integral from a to b of f of x is the limit as n goes to infinity of summation I equals 1 to n, f of xi delta x, where f of xi delta x is the area of a rectangle on a subinterval, and here we have n subintervals. So for example, let's take a look at this picture. If we want to integrate f of x over the interval a to b, we want to subdivide this region into rectangles, take the area of each rectangle, and then take the limit as the number of rectangles goes off to infinity. So our actual area is this limit of the Riemann sums. What I drew in this picture in the purple are left-hand sums, but actually any Riemann sum would do here. Remember that with this, delta x, the width of the subinterval, is b minus a over n. b minus a. N is the number of subintervals, so b minus a over n is your delta x. Now we're going to use the same notation here, delta x equals b minus a over n, but we're not going to always be using rectangles. We're not going to necessarily have a left-hand sum or a right-hand sum. We're going to have a couple of other methods. So the first method I want to talk about is the midpoint rule. So for each of those rectangles that we're subdividing, we are using the function's value at the midpoint of that interval. So from x0 to x1 on this subinterval, I find the midpoint, that's x0 plus x1 over 2, right? It's the average of those x values. I evaluate the function at that point, and that is going to be the height of the rectangle on this subinterval. Same thing's happening here. Now I need x1 plus x2 over 2. That's the x value of the midpoint of that subinterval. And I'm going to evaluate f at that point to get the height of the rectangle that we're using for that area. Remember that these are approximations and we're not taking a limit as n goes to infinity. We're taking a finite number of subintervals. So that's why we have the squiggly equal sign here. We're saying that this integral is approximately equal to, and then we have this finite sum that we're using. And the midpoint rule looks like this, f of xi minus 1 plus xi over 2. And we're multiplying by delta x, that's the width of the rectangle, right? This is the height of the rectangle, and then we're summing up those areas. So for this example, integral 0 to 2 of e to the x squared, we want to approximate using the midpoint rule and 4 subintervals. So let's take a look at our interval. We're given from 0 to 2, so I'm going to set up on a number line. This usually helps me to see what I'm doing here. So I set up from 0 to 2, and then it says delta x is b minus a over n, that's 2 minus 0, n is 4 subintervals, that's 1/2. So my x0 is always a, that's 0. So I'm going to mark at 1/2. I'm going to move over a half, and then another half, and another half, and I'm here. So this is our x0, this is x1, this is x2, x3, and x4. And the midpoint rule says we're not going to evaluate at those x values, but rather on the midpoints of those intervals. So rather than evaluate at 0 or 1/2, we're going to evaluate at the midpoint there, which is 1/4. Now, I think it's kind of easy to see that the midpoint there is 1/4, but in general, how do we get that midpoint if the computation isn't quite so simple? We're going to add together the x values, divide by 2. So between 1/2 and 1, we do 1/2 plus 1 over 2, that's 3/4. For here, we've got 1 plus 3/2 over 2, that's 5/4. For each subinterval, it's xi minus 1 plus xi over 2. So those are the values at which we're evaluating. So we're going to have f of 1/4 multiplied by delta x, the width of the subinterval, right? The width of this rectangle is going to be 1/2. And then we're going to have f of 3/4, which is the height, multiplied by 1/2, f of 3/4 multiplied by 1/2, f of 5/4 multiplied by 1/2, f of 7/4 multiplied by 1/2. So we would now evaluate in the function that we have, which is e to the x squared. And on your exam, you could leave it like this. If you could simplify any by doing anything up here, you could do that as well. That would be great. But otherwise, you can just leave it like this on an exam since you won't have a calculator. But since we have a calculator now, I could figure it out, 14.486 approximately. And that's the midpoint rule approximation to the area under the curve e to the x squared from x equals 0 to x equals 2. Notice in the formula here, I actually had a sketch of my f of x. It's not necessary for us to know what f of x looks like. It's more important that we just know how to deal with these x values on the interval 0 to 2. Now let's take a look at another integration rule, the trapezoid rule. With this rule, on each subinterval, instead of taking the area of a rectangle, you're going to take the area of, you guessed it, a trapezoid. So if we zoom in a little bit here, we can see that the black curve here, that's our original function. But what we're approximating is an area using a linear segment connecting these 2 points. So we're at x0, f of x0, and x1, f of x1, and we're using a linear segment to connect that. That gives us a trapezoid. And so that's the area that we're looking at. So what's the area of a trapezoid? Area of the trapezoid is 1/2 height times base 1 plus base 2. And that's usually when we see the trapezoid laying flat like this. We kind of have our trapezoid on the side. So what does that area look like in terms of our notation? The height here of our trapezoid is actually our delta x. And our base 1 and base 2 are actually f of xi minus 1 and f of xi for each subinterval, on the ith subinterval, I should say. So our trapezoid rule is going to look like what? We're saying that that definite interval is approximately equal to. We're summing up the area of the trapezoid on each subinterval. So the area formula has a 1/2. The height we said was delta x, so we've got 1/2 delta x, base 1 plus base 2. And this is I goes from 1 to n. Now if we expand this out and combine like terms, it's going to look like this. We're going to have 1/2 delta x. Your f of x0 is going to come up only once, and your f of xn comes up only once, but the middle terms, the f of xi in the middle, come up twice with this calculation. And so you've got f of x0 plus 2, f of x1 plus 2, f of x2, dot, dot, dot. All those in the middle get multiplied by 2. You have plus 2, f of xn minus 1, and then plus f of xn. So this is the formula that you'd want to remember for your trapezoid rule. So this delta x is b minus a over n. So the 1/2 delta x is going to be b minus a over 2n, and that's your trapezoid rule. So now let's take a look at what this looks like with the example that we were using before. We're integrating e to the x squared over the interval 0, 2, right? So let me just scroll down a little bit. This is the integral that we're looking for, and we want to now use the trapezoid rule. So we saw before our interval from 0 to 2 and our subintervals then, since delta x is b minus a over n, that's 2 minus 0 over 4, that's 1/2. We know that we're going from 0 to 1/2 to 1 to 3/2 to 2. So we know that we have x0, x1, x2, x3 here, and x4. And again, because the interval is 0 to 2, it's kind of easy to see what those points should be. But in general, I want to give you a formula to use for all of your approximation methods, including the midpoint method, this trapezoid method, and the one we're going to do next, which is Simpson's rule. We could always find xi by using the formula a plus I delta x. So x0 is always going to be a, and in this formula, that would be a plus 0 delta x. So that's a. In this case, that's 0 for us. x1 is going to be a plus 1 delta x. A is 0, so that's going to be 0 plus 1 times a half, which is 1/2. That's x1. x2 is going to be a plus 2 delta x. In this case, 0 plus 2 times a half, that's equal to 1. That's here. You could always use this formula to find your xi values. And for intervals that aren't so simple like 0 to 2, I encourage you to do that. But anyway, let's go back to what we were doing here, trapezoid rule. So let's take a look at the trapezoid rule. B minus A over 2n on the outside. So B minus A over 2n for us is 2 minus 0 over 2 times 4, 2/8 or 1/4. That goes on the outside. And then what's inside the parentheses? F of x 0, and at the very end, f of xn, and all the ones in between get a factor of 2. So that means we're going to have f of x0 plus 2 f of x1 plus 2 f of x2 plus 2 f of x3 plus f of x4. So that's going to look like f of 0 plus 2 f of 1/2 plus 2 f of 1 plus 2 f of 3/2 plus f of 2. So remember that this is our x0, x1, x2, x3, x4. So we'll evaluate here. We'll plug into e to the x squared. 0 squared is 0. E to the 0 is 1. We can simplify that. 1/2 squared is 1/4. We can simplify that. 1 squared is 1. So we could do a little bit of simplification. On an exam, I would say leave it here. And notice, this approximation is very different than the one we got before. We got 14 something before, and now we have 20.645. That's very different. And the reason for that is, well, first of all, these methods are very different, but also because we only have n equals 4 subintervals, and that's a very small number of subintervals. To get anything realistic, you'd probably want to have something like 100 subintervals and have a computer do it. Now let's take a look at Simpson's rule. This is the third approximate integration method that we have. Now Simpson's rule is a little bit different. On each 2 subintervals, Simpson's rule fits a parabola through the 3 points and finds the area under the parabola. So for these first 2 subintervals in this picture, Simpson's rule takes these 3 green points and fits the parabola through it and finds the area beneath it. And then it goes over to the next 2 subintervals and takes those 3 points and finds a parabola through those 3 points and takes the area underneath it. Now, first thing we notice is that in order to use Simpson's rule, we have to have an even number of subintervals, right? N must be even in order to do this. Second thing I want to mention is that even though Simpson's rule does find a parabola and find the area beneath it, we do not need to find the formula for each of those parabolas. This is something that comes up a little bit more in numerical analysis class, Math 328, but right now we're not going to worry about that. If you're curious about how that works, I can just scroll down here for a second. As a side note, how to fit a parabola through 3 points. If you've got these 3 points that you want to fit your parabola through, remember that your general formula for a parabola is going to have 3 coefficients that need to be found. Well, we have 3 pieces of information that's going to allow us to find those 3 coefficients. Plugging in x1, y1, x2, y2, x3, y3 gives us 3 equations in 3 parameters, 3 unknowns, a, b, and c. So then we can solve for a, b, and c with that. But again, this is not something that we need to do here. It's already done for us in Simpson's rule, and the area is found underneath it, so all we have to do is use the formula. So we're just going to jump right to this, and this is our formula for Simpson's rule. And I'm sure that they go through more details in your textbook, but I'm not going to test you on those details. So for Simpson's rule, we have b minus a over 3n on the outside, f of x0 plus 4f of x1 plus 2f of x2 plus 4f of x3. So we're alternating 4s and 2s here. And at the very end, we have a coefficient of 1. So we've got 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1, right? The alternating 2s and 4s in the middle for as many as we need. So what does this look like for our integral? Same integral we're trying to approximate from 0 to 2, e to the x squared. So our formula says b minus a over 3n. So b minus a over n we know is b minus a, this is over 3n, this is 2 minus 0 over 3 times 4, 2/12 or 1/6. So that's that 1/6 here. And then we have a 1, 4, 2, 4, 1 as our coefficients, evaluating at, again, this is x0, x1, x2, x3, and x4. And again, we simplify as much as we can, and we would leave it here on an exam. So I just want to point out, just as with Riemann sums, the more subintervals we use, the better the approximation is going to be. So for sure, keep that in mind. Now let's take a look at another example. I'd like you to compute this integral exactly and then approximate it using the midpoint rule with n equals 3 and using the trapezoid and Simpsons rule with n equals 6. So please pause the video and work on that. Computing this integral exactly, we first write the 1 over x squared as x to the negative 2. Integrating, we get x to the negative 1 over negative 1, which is negative 1 over x. And plugging in our bounds and subtracting gives us 3/4. And so that's our exact answer. Now, using the midpoint rule with n equals 3, since n equals 3 and our interval goes from 1 to 4, we know that we're going to have integer values for these xi. So x0 is 1, x1 is 2, x2 is 3, and x3 is 4. But if that's not clear to you, then of course we can use the formulas xi is equal to a plus I delta x, and delta x is equal to b minus a over n. So b minus a over n is 4 minus 1 over 3. That's 3 over 3, or 1. That tells us that's the spacing in between the x values. That's the width of the subinterval. Now we want to add on multiples of this to our a value. A here is 1. That's the lower bound for our integral. So we have xi is equal to 1 plus I times 1, or xi is equal to 1 plus I. So x0 is just 1, x1 is 2, x2 is 3, x3 is 4. So that's how we get these values here. Now keep in mind that the evaluation points for the midpoint rule are the midpoints of these intervals. So we're not going to be plugging in 1, 2, 3, or 4. We're going to be plugging in the midpoints of these intervals. So between 1 and 2 we have 3 halves. Between 2 and 3 we have 5 halves. Between 3 and 4 we have 7 halves. And so our midpoint rule approximation looks like this. We have delta x multiplied by the sum of f, our function evaluated at those midpoints. So delta x is equal to 1, so we have a 1 outside, and then we're plugging 3 halves into the function. So that's 1 over 3 halves quantity squared, plus 1 over 5 halves quantity squared, plus 1 over 7 halves quantity squared. Simplifying and combining our fractions, we end up with 7,564 over 11,025, which is approximately 0.686. And we know that our exact answer was 3/4, which is 0.75. Let's take a look at the trapezoid rule. We said here we'll use n equals 6. I only chose n equals 3 for the midpoint rule because I knew this was going to be very messy. Here we have n equals 6 for the trapezoid rule. So from 1 to 4 we have 6 subintervals now. So delta x is 4 minus 1 over 6, or 1/2. And these give us the xi values. And the trapezoid rule says we're going to have 1/2 delta x multiplied by f of x0 plus 2 times f of x1 plus 2 times f of x2 plus 2 times f of x3 plus 2 times f of x4 plus 2 times f of x5 plus f of x6. So plugging in, we're here. Our delta x is 1/2 in this case. And then simplifying, we're here. And we get an answer that's approximately 0.789, which is closer to our exact value. And now using Simpsons rule, the interval setup is the same. We have the same delta x here, but our formula is a little bit different. We have a 1/3 delta x, and then we have different factors. So evaluating and simplifying here, we get an answer that's approximately 0.755, which is even closer to our exact value of 0.75. Now let's talk about some error bounds on numerical integration. Often what's of interest to us is to find the number of subintervals we need to use with our approximation to get a certain degree of accuracy, or to get an error smaller than a certain amount. So we have these error bounds here that we don't need to go into the derivation of, but we'll just use these formulas. Suppose f double prime is continuous on AB, and f double prime is bounded in absolute value. It's less or equal to k for all x in the interval AB. So now we're integrating f over the interval AB. Then the error associated with the trapezoid rule with n subintervals, that error in absolute value is less or equal to k times b minus a to the third over 12n squared. And the error using the midpoint rule with n subintervals is less or equal to k times b minus a to the third over 24n squared. So notice that generally speaking, the midpoint rule is going to have half the error bound that we have for the trapezoid rule, right? Because we've got a dividing by 12 here, dividing by 24 here. So that says that generally the midpoint rule is going to be better. And then for Simpsons rule, we want to suppose that the fourth derivative of f is continuous on AB, and in absolute value is less or equal to L for all x in AB. Then the error associated with the Simpsons rule with n subdivisions is less or equal to L times b minus a to the fifth over 180 n to the fourth. So how are these error bounds useful for us? So for example, here we want to find the number of subintervals n so that the approximation to the integral 0 to 2 e to the x squared dx, so this is the integral we were approximating before, we want to use the trapezoid rule with an error less than or equal to 10 to the negative third. So we look at this rule that we have, we know that the error in absolute value is less or equal to this. Now if we could get this amount less or equal to 10 to the negative third, then we're good. So that's what we're going for here. So we say we know this error in absolute value is less or equal to this, so if we could get this less or equal to 10 to the negative third, then we're good. So what do we need in order to make this inequality here? We need a k value, which is a bound on the absolute value of the second derivative. So let's take our second derivative. We've got f of x equals e to the x squared. By the chain rule, f prime is 2x e to the x squared. And then by product and chain rules, we get our second derivative, which I wrote in factored form, 2e to the x squared times 1 plus 2x squared. Now we want to bound on the absolute value of the second derivative here. The first thing I notice here is that if we've got 2e to the x squared, this factor is always going to be positive, right? E to any power is positive, times it by 2, it's still positive. Also look at what we have in here. Even though our x values are positive, it doesn't even matter, we're squaring them. Multiplying by 2 and adding 1. This is also strictly greater than 0. So our product is strictly greater than 0, and we could actually drop the absolute value sign on our second derivative. So we need an absolute max of our second derivative on 0, 2. So how do we find an absolute maximum? We have to check any critical points within the interval and test the endpoints to see what's going to give the maximum value. So if we're looking for an absolute max of this function, we need its derivative, which is the third derivative. So we find the third derivative, and we want to know where this is 0, if anywhere. Because remember, that would find us a critical point, and that would help us find our absolute maximum. But we notice when we find the third derivative of f that for x in 0, 2, we've got 4x greater than or equal to 0, e to the x squared strictly greater than 0, and 3 plus 2x squared strictly greater than 0. So f double prime is then increasing on 0, 2. If its derivative is greater than or equal to 0, it's increasing, or I should say maybe non-decreasing, on 0, 2. That means its maximum value, its absolute maximum, has to happen at the rightmost endpoint, has to happen at x equals 2. If it's an increasing function, the maximum value is going to occur at the rightmost endpoint. So let's take f double prime of 2, 18e to the 4th. That can serve as our k. Now we go back to the formula for the error bound on the trapezoid rule, and we're using 18e to the 4th as k. And we put in our b minus a, which is 2, and we have 12n squared in the denominator. Remember that we're solving this now for n. We're trying to find out what's the number of subintervals we need or to get our error to be less or equal to 10 to the negative third. So we simplify a little bit more here. Solve for n, we get n has to be greater than or equal to 809.43, so let n be greater than or equal to 810 subintervals, and that's going to give us the number of subintervals we need for this approximation. Let's take a look at one more example here. Oil leaked from a tank at a rate of R of t liters per hour, where the graph of R is shown below. Use Simpsons Rule to estimate the total amount of oil that leaked out during the first 6 hours. Okay, they're giving us the graph of a function that is a rate of change, right? This is leaking at a rate of R of t liters per hour, and they want to know the total change, the total amount of oil that leaked out. So we need to estimate the area under this curve, because recall the integral of the rate of change function from a to b is the total change over that interval. So we need to integrate here R of t from 0 to 6. So we want to find the area under this curve from 0 to 6. And they're asking us to use Simpsons Rule. Now we know with Simpsons Rule we need to have an even number of subintervals, and since we're going from 0 to 6, we might as well take 6 subintervals. So here's our formula for Simpsons Rule in general. And then for us, we have a equals 0, b equals 6, and we're going to use 6 subintervals, so n is equal to 6. So that tells us that x0 is 0, x1 is 1, x2 is 2, and so on. And so the evaluations we need to make look like this. Now, how are we going to evaluate R of 0, R of 1, R of 2? We don't have exact values here, but we're going to approximate them given this graph. So for R of 0, it looks like R of 0 is equal to 4, and R of 1 is equal to 3. R of 2 looks like it's approximately 2.4. So R of 0 we said looks like it's 4, R of 1 is approximately 3, R of 2 approximately 2.4, and so we're estimating here these values from the graph. R of 3 looks like approximately 1.8, R of 4 approximately 1.5, R of 5 approximately 1.2, and R of 6 looks like 1. And so we're here. And then we just simplify, and we get approximately 12.27 liters. So this is an example of how we're using approximate integration when we don't even have a formula for the function. So in this case, we're given a graph and we're getting these values off of the graph. Sometimes instead of the formula, they would give you a table of data, and you can get these values off of the table of data. And with this, we'll conclude our lesson on approximate integration.